our next speakers, which is Anthony and Ari with Novo Nordisk, and they're going to let us know about how they're using LLMs as well. So with that, I'll pass it over to Ari.
Yeah, thanks, Phil. Thanks for having us. Just get the great. So there must be a lot of savings to find in programming. This is some of the things that we hear every day now with AI being pushed out into LinkedIn, where our managers can see it. And I would say in pharma, there is actually some business cases where it makes sense to look into generative AI. So in pharma, it's a standard that you do double programming to do kind of code validation, and that is a resource-heavy process. You basically use two people to generate the same piece of code. And internally in our company, we see an increase in the number of trials, which means that we need to have a higher throughput and output of the code we generate. And in general, if we see programmers working on multiple trials and even multiple therapeutic areas where managers maybe want to move them around, we also see a need for support in switching between these contexts of programming in maybe a clinical pharmacology trial over to phase 3A trial. And this is just to highlight, so when we do programming kind of on the clinical trial pipeline, we do code for STDM, we do code for analysis datasets called ADaM. They're governed by industry standards. We do code for TFL, and we even do code to kind of compile all of this into reports and submission packages. So there's a lot of places in the clinical trial pipeline where we could apply generative AI, and especially in the coding space. And we have, for the past 6-7 months or so, been looking at how we could do this for our analysis data sets. So how could we look into programs, how we generate data, and how we utilize metadata. So I just want to show you how we designed a new ADaM process. So what we used to do before, also when we were primarily using SAS, was that all the metadata we needed to generate data sets, they were managed in this single Excel file that we could also generate a defined XML file from. And then we had a small set of like standard macros, support macros that we could utilize in larger scripts for creating ADaM datasets. And what we want to move to now is that we actually want to switch out this Excel file with metadata as YAML files, where we have one YAML file per domain. And right now we're building an R package to kind of build a toolkit for working with YAML files. The thought behind this is also that it's easier to provide YAML as context in a generative AI setup instead of Excel files. We're also now building out kind of a standard suite. So you might know the Admiral package from Pharmaverse, and we want to build an even kind of higher order component on top of Admiral that utilizes multiple Admiral functions, and pair it with a standard test suite that we can use to alleviate some of this double programming burden that we see. And we then want to bridge this gap by having trials build kind of custom components with their own tests. All of this we want to orchestrate into a single test suite for the programs that we generate, and then the program as output. And this is something that we're building now, but we can look into where can AI help in this new process of generating ADaM. Well, there will definitely be a case where we want to build the metadata, because this will be the engine of how we orchestrate all these things. We could also see a scenario where we want to use generative AI to build up our standard library based on historical code. We could also use it to bridge the gap between standard and custom code that's being built out on the trial. And We can use it to build full programs or even review and write tests for our programs. So we've been building a proof of concept here where we have the biometrics organization inside of Novo Nordisk. We have some AI capabilities, and then we have Microsoft's solution engineering, industry solutions engineering, helping us try and build a proof of concept. And we've decided on this kind of high-level overview here where we used YAML files, so the specification for each data set, to build full programs, but try to design it, have the model designed in such a way that it could fit into this future framework. And then we wanted to review and write tests for it. So what we think happen when we start a project like this is that there is, of course, a lot of historical input because we have executed many clinical trials. And I think it's the same thought that our managers and leaders have that, well, if you just take this historical input and give it to generative LLM, you automatically or magically get full programs and you can review and write tests and it will be completely according to spec. But reality is very different from this. So what I found out also in our journey from switching from SAS to R is that if we want to generate R-based programs, we actually need to build up a solid database of what we call ground truth. So R code that represents the way we do programming in Novo Nordisk. And also working with other data scientists across the organization, because we work on clinical trial data, there will almost always be data access issues. So if you want to build something where you test that you actually get the same output as a good old-fashioned programming, you need to have data available. There's also that we are very ambitious in what we want to do in Novo Nordisk, so we are changing multiple processes also around the programming setup at the same time. And that could also kind of set ourselves up for some scope creeping because we couldn't completely align what it is we want to achieve with this proof of concepts. And another thing that we find through these experiments is that even though we thought that we were very good at documenting all the things that happen in the code and what needs to happen in metadata, much of that knowledge actually still lies in the brains of our programmers. So there's a kind of cultural knowledge that hasn't been documented in either the metadata specification or something like the analysis data reviewers guide. And then there's always this problem with, well, if we build a product, how do we integrate it into our current setup that needs to be GXP compliant? So these are some of the things that we are actively working on currently to make the experimentation process easier and the product better. And Anthony, he will tell you a little bit about what we've actually been building on the engineering side.
Thank you very much, Ari. Yeah, so here we have kind of an overview of what we envisioned to implement. So as Ari mentioned, we've been working with these metadata YAMLs that sort of consist of what might look like LLM instructions. So they're quite rich in rules to implement on the existing coding base and data models, along with some context around the rules that are being required of a model. So if I take you through the execution flow of our multi-agent workflow of what we envisioned, that was inputting documents like the ADRG, the reviewer's guide, protocols, statistical analysis plans. This goes into a RAG agent. If you're not familiar with RAG, it's a sort of standard tool now to allow large language models to ingest long documentation. So you can just think of it as a component where we can take in longer documentation than a standard context window. We also have a historical code agent. So this can search code bases within our organization that sort of contain best practices, standard approaches, coding styles, and feed this as instructions into the model as well. And then we pass this through to a code generation agent, which works in tandem with a reviewer agent to generate code and refine it based on the specification. So the reviewer agent might have a list of criteria. We might execute some validation metrics on the code that's generated and pass these outputs to the reviewer agent. And then this can be fed as feedback to the code generation agent and also reviewed by the human guide. On the next slide, I think we discuss orchestration, because unlike a deterministic machine learning program, these agentic workflows need some degree of orchestration. So some people here may be familiar with the concept of MCP. We had a presentation, I think, that involved tool calls in the last hour and discussed how you can provide LLMs with tools. You can do this locally with code you expose to the LLM, or you can host this code on a remote server and give the agent on the client side the opportunity to execute that code on the server by passing inputs, the function parameters, and then returning the outputs from the server to the client. So it's just a sort of layer of abstraction that we'll reference a lot in this talk because it's a new tool that we're working with Microsoft to try and understand where are the opportunities to apply this MCP concept across the clinical pipeline. We're going to talk a lot about GitHub Copilot as well, but there's nothing really specific in what we've implemented to this LLM client. You could use Klein or RuCode or your preferred chatbot framework, as long as it has this MCP connectivity. And we'll also talk about how we implemented this in VS Code. But again, the choice of IDE is not essential to the implementation that we've made. So you can see two orchestration approaches here, where if you're familiar with using GitHub Copilot, you chat to GitHub Copilot, and the user experience is that they will maybe ask to generate R code for a specific domain or a specific data table in this data model. And the agent will go away and call a sequence of tools. And you can see the tool calls that are made. You can see the inputs that go in. You can see the inputs that go out. You have a lot of visibility of the process. The other approach that we took was we were using a software development kit from Microsoft called Semantic Kernel, which has been sort of developed in tandem with GitHub Copilot, but leverages additional functionality and sophistication that you might see in frameworks like LangFuse or LangChain. These are the open source products that allow you to make sophisticated agentic frameworks. So where you can see on the top for orchestration, we have a very linear flow that represents and sort of mimics a linear chatbot experience. The semantic kernel is a more sophisticated framework where we can pass our context to a group chat manager. And then effectively you have something like a Facebook Messenger group chat where lots of different agents are posting into a shared context. And then this manager takes all their inputs and outputs, summarizes them, and passes them back to the model. And then we do have an agentic framework for directly querying the user for feedback, because what you lose from this approach is the direct integration with the user. So a bit more of an overview on the next slide, I think. So yeah, you can see here how a user might interact with the framework that we've created, where at each stage there's a tool call, and between the user and each tool is GitHub Copilot. We can pass in an instruction file as context as well. So this might look something like a system prompt. If again, people are familiar with how LLMs use system prompt to continuously maintain some kind of context throughout the whole chat history. And we have this linear execution of the generation flow. And by the end, after reviewing the code, we should have a somewhat sophisticated first draft of the code that we need to execute on our clinical data. Semantic kernel, by contrast, we have a lot less user and agentic interaction. So you can see that there's just a sort of start execution call. Then we jump into the group chat manager, and the group chat manager will interact with a sequence of agents. They'll all work together. They'll pass context between each other. There'll be some kind of orchestration done by this semantic kernel SDK. And anytime there's maybe some unsurety, we can program in this kind of behavior that there's an agent that can query the human, and at that point the human can give some directional feedback. So our big question was kind of, what is the better way to do this? Where is a better place for the orchestration to live? and where is a better place for us to run the orchestration from for this process. And I think we've done some testing of this. We've done some user feedback as well. So there's lots of things that go into this. It's an engineering question. It's a data science question. It's a UI UX question. But I think it was a good reflection to think about an abstraction of this process that we've undertaken and the framework we've built, because we have our SMEs, they're our subject matter experts. So these are the clinical data scientists that we've been working with over the course of this project to interact with and understand their particular working patterns, behaviors, and preferences. They will interact with an MCP client. So this would be GitHub Copilot on VS Code, or other IDEs and LLM clients are available. This GitHub Copilot talks to a remote server, which we've built. And the remote server can come and pull from some kind of file storage that we've created, which is maybe where we put our trial documents, our protocols, historical code, things like this. So on the next slide, we can see that it's kind of natural that then you can characterize how data flows between these different concepts. So the user will chat with GitHub Copilot. GitHub Copilot talks to the server, it calls tools, it receives the output. And sometimes these are two-way relationships, but also we allow our SMEs to write to the file storage and update documentation, but we wouldn't allow the agents to we would only allow the agents to read the documentation, because we don't want AI overwriting what we consider our grounds truth or standard of truth. So on top of these different technical concepts that we've built, the sort of abstract concepts around the behavior of these components. So the SMEs sort of represent our institutional knowledge. That's our internal conventions, regulatory preferences that we're aware of, but might not be written out explicitly anywhere. Coding styles that we internally prefer and that they have worked with historically. The context is represented by the file store. So this is our single source of truth. This is where we want everything to live that we consider to be the valid input for the model and that we want to draw from as reference. And the important thing is that it's immutable at runtime. So we don't have the opportunity to overwrite this data. This doesn't represent a dynamic environment where agents are reading and writing or the user's doing the same. That instead is the MCP client. So there's a dynamic live workspace, and this represents the state of our process. So code is being written here. The validation results are also being returned here. Intermediate output is being stored here. So this is where data is created, stored, and deleted. And then finally, we have a code generation engine on the MCP server. So then this is where all of our business logic is containerized. So this is where our prompts are. This is where our agents are implemented, our functions, which we consider validation tools, but also we can expose other functionality. For example, we're working on remote code execution. So we want our agents to generate our code and then execute it behind the scenes to test its validity before returning it to the user. So this is a kind of natural separation we felt. And then where our GitHub Copilot semantic kernel approach kind of sits was kind of obvious, because on the next slide, you can see that the GitHub Copilot orchestration kind of represents orchestration living on the MCP client. So the chat is making individual tool calls. The user has all this visibility we talked about, and that's a great way to catch hallucinations, or if the code is pointing to the wrong directory for historical code, for example, and we have this nice linear flow of execution. But unfortunately, we have a high latency in our UX experience. You kind of wait a couple minutes for an agent to execute and return you the output you want. So you're kind of sitting around waiting for 2 or 3 minute intervals consistently, and you kind of lose the joy of the coding experience and feel that there's a feeling of debugging code rather than writing code. So that's something definitely we're trying to tweak our tools and their functionality to understand maybe how we can create a better experience for the users. And then by contrast, on the semantic kernel side, we just call a single MCP tool, and all this brilliant orchestration happens behind the scenes, but there's no clear termination to the orchestration until a very complex thing is returned. There's a group chat that manages this context and then sort of inwardly decides what's acceptable and what meets the criteria. We have these sort of clunky manual callbacks where we can receive input from the agent, from the user through an agent, but it's not as sleek and sophisticated as GitHub Copilot. We don't have this nice UI that they have. And so we are kind of trading off by also using this more sophisticated tooling behind the scenes. And finally, because there isn't this visibility, we have errors cascading through the generation that you can only catch after you've run a 10-minute process in the background and then seen, oh, this was a typo from the start, or I uploaded the wrong file, or something else went wrong in the process. So that was just kind of one overview of where we're at conceptually. I think there isn't really a right answer, and it's definitely one thing to think about when you are creating your agentic flows, when you are building these multi-agent systems, is where do you want your user to sit? What do you want their experience to be? Some cool stuff we didn't get to talk about. We've been working on A/B testing, monitoring LLMs, RAG workflows for parsing documentation and working with specific internal R packages. And I think finally, we'd just like to thank all of the technical contributors to this project. Not of all are here today, but we have internal colleagues, Mike and Paul, and also a host of people from Microsoft who supported us on engineering a fantastic product that we've been able to demo to users in a very short amount of time. Okay, thank you very much.